Hello, and welcome to the lecture for Chapter 9 from Astronomy OpenStax. This chapter is titled Cratered Worlds, and what that tells us is this chapter is about the Moon and Mercury. So that's Earth's moon, which is, of course, just known as the Moon, and Mercury. So really, the title of this chapter could be The Moon and Mercury. All right. So we're going to first talk about the moon. We're going to spend some time talking about the moon and cratering and understanding a world like the moon, and then we're going to compare it to Mercury, and then we're going to talk about some specific details of Mercury because Mercury is a very interesting planet in its own right. Now, humans have been to the moon. Okay, it's the only place where humans have set foot other than planet Earth. All right, here's a picture of an astronaut on the moon. Okay. Now, there are two faces of the moon, two sides of the moon. We have on the left, we have the hemisphere of the moon that faces Earth. Okay, there are Maria, which are these large dark regions that are visible in this picture. All right, and then the image on the right, well, that image shows the hemisphere that faces away from Earth. Okay, that part is dominated by the highlands. Okay, and then to get an idea of this asymmetry, the difference between the two sides of the moon relative to Earth, it's helpful to understand the physical processes that would make this difference possible. And that is the tidal friction between Earth and the moon. Over millions of years, the moon got into the current orbit that it's in, which is called a tidally locked orbit. That's why we have one side that always faces us. In other words, and we've talked about this in previous chapters, in other words, the day of the moon and its year or its orbit are the same. Okay, so the orbital period, I call it the year because that's how long it takes to complete an orbit. Of course, calling it a year is incorrect because the moon doesn't have a year; it has an orbital period around Earth. But where there's the orbital period is equal in time to the day. Okay, the lunar day, the time for it to spin completely around on its own axis, is exactly equal to the time it takes to orbit all the way around Earth. And actually, they're not exact. Let me be clear on that. But they're very close to each other. There's a little bit of variation, so we see some extra bits of the moon on the sides, depending on the particular time of the year on Earth. But overall, there's always one side that faces us. And because of that process that has led to the moon being tidally locked, due to the energy associated with pulling the oceans and the oceans resisting being pulled. Those are Earth's oceans, of course. The moon does not have oceans. But that process has led to one side of the moon, early in the moon's history, being warmer than the other side. And warmer by a tiny amount, but possible so that lava could flow more readily on the side of Earth or the side of the moon, excuse me, that was always facing Earth. Okay, so again, it's the tidal locking, it's the orbital properties of the moon that lead to the asymmetry between one side of the moon where lava flowed and filled in craters, and the other side of the moon where that practically did not happen, and we're just left with craters on highlands, no low parts of the moon's crust. Okay, so lava filled in craters, creating the Maria. That's how they were created. This would have been billions of years ago, early in the moon's history, but the same physical processes that led to the moon's unusual orbit are those that led to one side having more lava flows than the other. Okay, the side that faces us. Now, here we have a picture of a scientist on the moon. Interestingly, of all the astronauts that went to the moon with the NASA program, and no other space agency has sent any people to the moon to date, only one of those astronauts was actually a trained scientist, and that was geologist Harrison Schmitt. Okay, and this geologist in this picture is taking a look at a large boulder. Boulders like this, as well as the mountains that we see in the distance of this photo, or in the horizon of this photo, these types of objects, whether they are the mountains or the boulders, are all created by the overall, the dominant form of geology on the planet, on the not the planet, but on the moon, on the world, the moon. And there's just one dominant type of process, and that's impacts. Okay, so the same impacts that make all of the craters that we see on the moon, and those are impacts because of asteroids and comets crashing into the moon, leaving these large craters. That process dominates everything about the moon's surface. The very fact there are mountains are because of dust, the regolith, which is the type of dust that exists on the surface of the moon, getting thrown up by those impacts and by the energy released in those impacts, that dust getting thrown up and deposited into mountains. Okay, the fact that there's a boulder sitting here was because it was thrown due to the energy associated with an impact. Okay, either an asteroid or a comet smashing into the surface of the moon. So we can really say that with very few exceptions, everything we see on the surface of the moon is dominated by impacts. Now, sometimes there's some other part of that story, another phenomenon, because of course the Maria, which are ancient, again billions of years old, they were originally created due to an impact, or they were triggered due to an impact, but then it was the heat energy under the surface of the moon that allowed lava to slowly flow up and then fill in these regions. Okay, but they started with an impact. So we can really say there's a common story to the moon. It's all about impacts. The surface is governed and dominated by the process of impacts. Okay, now of all those astronauts, one of them being a scientist that have gone to the moon, they've brought back a lot of lunar rocks, hundreds of pounds of lunar rocks, hundreds of kilograms of lunar rocks that have been investigated with scientific methods for decades now. Now, of course, we see an older picture of a technician with the Apollo project examining one of those lunar rocks. They keep them isolated so that they don't interact with Earth's chemicals, so we know exactly what their chemical properties are without polluting them with Earth's chemicals. Okay, but what's interesting is this photo is so old, as you can tell, but I feel like that's fairly appropriate because we haven't brought back any new rocks from the moon since the 1970s. So it's appropriate that we're looking at an old photo, even though there's still ongoing research with some of these rocks, because there's been such a large gap in actually collecting more rocks from the moon or ever returning to the moon for any sort of scientific mission. Okay, now what is interesting about these rocks is they are subtly chemically distinct from rocks on Earth. They're similar to the rocks that we'd find in our own mantle or crust of the planet Earth, but they have some subtle chemical differences, so we can always tell them apart from Earth rocks. That even extends to the idea that with certain asteroids that land on the surface of the Earth, sometimes we can tell that these are ones that came from the moon. You might wonder, how would an asteroid come to Earth from the moon? Well, if there's an impact with the moon, then some of the large boulders like this don't get redeposited on the moon, but actually get thrown off into space with an escape velocity sufficient to leave the moon, and then they might then later get pulled into Earth's gravity and then crash into Earth. Now, when we did travel to the moon, when the NASA program traveled to the moon, they used rockets like this. This is one that was never used, the Saturn V rocket. Okay, this was a amount of energy that a rocket had never had up to that point, okay, and really has rarely had since, because there's been few cases where we've needed to launch rockets with such a great velocity, because since then, in the many decades since the 1970s and the last lunar missions, we've mostly been sending things into orbit around Earth. We've been launching satellites. That's been the primary purpose of rockets, or launching scientists to go to the International Space Station. But we have not, for the most part, been launching rockets powerful enough to get to the moon or further out. Now, there are exceptions. We've launched some deep space probes and so on. But for the most part, we don't use rockets this large and powerful. Okay? Now, this is a recent lunar mission list from Wikipedia. And what this is showing is that in the last 7 years, since 2014, there have been continued missions to the moon. No manned missions, no missions that are actually sending people, right, men or women. But there have been probes, flybys, orbital space probes that actually get into orbit around the moon. So there have been lots of cases of those, but not primarily by the United States and NASA. We see that there was a test program that was successful. Looks like that was a flyby that happened in 2018. Okay, and I think that mission was doing something more than just looking at the moon, but it did fly by the moon. It probably took some more recent pictures of the moon. But we can see that certainly China has been very interested in the moon recently. As recently as November of 2020, we had a space probe land, I believe, on the far side of the moon to get lunar samples and make a flyby. So it's a lander. So this recent mission, that means it landed on the surface, and also sample return. So they're actually going to be bringing samples back. So even though they're not landing people on the moon, they're actually landing on the moon, probably with some sort of lander and rover of some sort that then can relaunch back up, because the escape velocity of the moon is not that great. The moon doesn't have nearly as much gravity as Earth's, so it's much easier than to launch back off from the moon. The same reason it's very easy to jump a huge distance on the moon. The gravitational acceleration on the moon is 1/6 that of Earth, so it's 1/6 as fast in order to escape it. So that's probably what this Chinese mission is doing, and then we're actually going to get some moon rocks back to Earth. We can see that other countries have even sent space missions to the moon. Luxembourg with Lux Space, which was a successful flyby back in 2014, and then Israel had a mission that actually failed on landing. It was going to be a privately funded lunar lander mission. But anyway, you can see that other countries, including India, by the way, this one failed, but this one is still operational, have been landing on the moon. Okay, all right, and orbiting it. So very, very interesting things going on, and it stands to reason that NASA or maybe some private organizations within the United States will be going back to the moon in the near future as well. There is some renewed interest in the moon. All right, here's a picture of a peaks of Tycho crater. So Tycho crater is one of the larger craters in terms of crater size on the moon. The larger size are the size in like the 80 to 110 kilometer diameter range, like Tycho, so one of the biggest ones. And these craters have basically mountains in the middle often due to the effects of the impact. There's all the dust gets thrown up, and then kind of some of it redeposits right in the middle of this very large crater. And that's what we're looking at here with shadows being cast. So the sunlight, of course, is coming in from this direction. All right. Here is a crater in the lunar highlands. So there are some lunar highlands on the side that faces Earth. If we go back and take a look, we can see the lunar highlands are not restricted to the far side of the moon, okay? But they are a lot more common on the far side. The far side of the moon is primarily highlands, as we can see. All right, so there's just a huge amount. Most of the surface are the lunar highlands. All right, and looking at those, that lunar highlands are covered in craters. All right, they're old and heavily cratered. And this actually leads us to an interesting bit of science about dating things, dating planets and worlds, so moons as well within our solar system, based on how many craters they have. Okay, and we'll talk more about that in just a moment. Here's another example of a lunar mountain, very smooth. Okay, that's because it's never been weathered, because the moon does not have an atmosphere at all. So there's no weather on the moon. There's no wind. There's certainly no water cycle with clouds or rain or anything like that. So there's no weathering of these mountains. They were deposited due to dust getting thrown up due to those impacts, and then have just remained that way ever since. Okay, unless some future dust gets redeposited on them. Okay. Here are those Maria I spoke about before, these large lava flows. They only cover about 17% of the moon's surface, but that 17% is entirely on the face that faces us. So when we look at the moon, they're quite noticeable to Earth-based observers of the moon, all right? And they're large flat plains of basaltic lava, okay? And from the Apollo missions, and maybe even these recent Chinese missions, we brought back rocks from the highlands as well, but also from the Maria. Here's an example of a rock from the Maria, all right? And we can see that it's clearly volcanic. We can see that it's volcanic due to all the air bubbles that formed in it. So it really confirms the idea that these were large lava flows that filled in craters, because those craters weakened the crust of the moon, and there was lava underneath the crust of the moon. Now, is that still happening today? Well, first of all, there's not as many large impacts today on the moon. Again, we'll speak about that in just a moment. But also, there is no more lava beneath the surface. Okay, there's no more magma beneath the surface of the moon. The moon has completely cooled. All models of the moon suggest that it no longer has a hot core. It is cooled all the way through. Okay, here is the Mare Orientale, which is a very interesting one because it didn't spread as much as other Maria. Perhaps it was at the tail end of when the moon still had lava beneath its crust, or again, magma beneath its crust. So maybe there wasn't as much to flow to the surface. So there was a small amount of lava that bubbled up and filled in the deepest part of the crater. But then we can see that then there's a part of the crater that collapsed. All right, and that's what happens just due to gravity. Even though it's weaker on the moon, there is still gravity, and the walls of the craters collapse in landslides, creating this tiered appearance, which we see here. Okay. All right, and the outer ring is about 1,000 kilometers, and I think that outer ring is might actually be due to some of the throw off. So as the dust got flung up into space, then it kind of created that outer ring because that's a huge, huge impact crater. But it's also perhaps just one of the largest impact craters on the moon. Here's a footprint as far as things impacting the surface of the moon. One of the only things that hasn't, besides meteorites and and comets and so on, are human footprints, right? So here's a pushing into that fine dust, the regolith on the surface of the moon, the lunar soil. All right. So for a long time, scientists, including at the beginning of the 20th century, so late 1800s, thought that the features of the moon were dominated by volcanism. What we were looking at was lots of volcanoes, lots of the tops of volcanoes, the calderas of volcanoes, and so the moon was just covered in them. There's this volcanic place, a bunch of mountaintops, right? And scientists genuinely thought that because it didn't stand to reason that those would all be impact craters. Why would the moon be covered in impact craters? If the moon is covered in impact craters, that implies that there's just things raining down on planets all of the time. In that case, why isn't Earth just being bombarded by meteorites all the time? Well, why is there no very little record of impact craters on Earth? Right? So scientists really genuinely thought that the planet or the moon was not dominated by impact craters. But now we take it for granted that it is, right? We look at the moon and we say, of course it's covered in impact craters. This is a typical impact crater. Why would we think otherwise? But it's just different context of assumptions. All right. At the, as recently as the 1920s, 1930s, scientists just didn't understand the importance of and the history of impacts within our own solar system. That there have been so many impacts over so many hundreds of millions of years, and that worlds like the moon and the planet Mercury were just covered in these impacts. Okay. Now, again, we don't see impact craters covering Earth because Earth has weather, right? Earth also has continental drift, right? So continents are being, often, crashed into each other. New mountains are being made, which would cover up craters. But even more immediate than the continental drift covering up craters, we have the simple process of those craters getting weathered by wind and water and glaciers, and they're rarely left behind, for at least rarely for an extended period of time. It's hard to find traces of craters in many cases. There are some in the desert that have lasted for a few million years, but those are the exception on Earth. Okay, but on the moon, they basically just last forever. There are no plate tectonics on the moon, and there's been very little volcanism except for the period on when the Maria were formed on the one particular side of the moon that faces us and got warmed up due to the tidal friction, okay, the orbital friction. So we understand that the moon is covered in craters. Okay, a little bit about crater formation is that craters are almost always perfectly circular, which is interesting because it's not as if a meteor is always going to come down, at a straight angle. They often will come in at curved angles. So why are there not a lot of craters that are stretched out to represent the angle of impact of the meteorite? Well, that's because these meteorites come in at incredibly high speeds, okay? So we're talking at about 4.2 kilometers per second as the minimum speed, and in many cases often around 14 kilometers per second as a typical speed. So it'll say average velocity. So these meteorites are coming in and hitting the moon as well as those that hit Earth at incredibly high speed. So when they come and they crash, it's not about them, basically pushing dirt out of the way due to their momentum. It's about them completely vaporizing. When the rock hits rock or hits any material, all of that matter is phase change. All that solid material is phase change into a gas because there's so much energy being released. And there's of course, solid pieces that get thrown off. But because we have a process that isn't dominated by momentum, but is instead dominated by energy, we have that the craters are almost always symmetric, okay? Because the energy spreads out in symmetric waves, okay? So that's why impact craters, despite many angles, even steep angles of meteorites coming in, always end up being perfect circles, okay? It's because of the energy process, because of the vaporizing of the rock, okay? When the crater is formed, it has a ridge, all right? And then some of that matter is redeposited, filling in the crater, so it's not as deep as, say, the moment after it's formed, okay? Because basically gravity pulls a lot of that rock back down. But sometimes there's big trails of matter that get thrown off way to the sides. So you can find rocks that came from that impact many, many kilometers, hundreds of kilometers away in some cases, okay? All right, so again, as I said before, this is a typical impact crater right here. All right, we can see how erosion and landslides occurred on the walls of the crater, and how there's some mountains that formed because of dust and rocks resettling right down in the middle. Okay, so we can date the moon based on the impacts. So when we look at the moon in these two beautiful images, which have another story to tell as well, but when we look at the moon in these two photos, we can see these large regions where the Maria, okay, exist, and that's where lava has flowed over large plains, are pretty free of craters. There's not many craters on them. Now there are some, right? There are some impact craters on the Maria. Certainly there are, right? We can see one right there, for example. There are plenty of examples of them, okay? But they're much rarer, all right? As opposed to the highlands. The highlands over here are just covered in impact craters. And we saw in the other photo that showed the far side of the moon was just covered in impact craters. So there clearly is a delineation between the Maria having fewer impact craters and the highlands having more, okay? Now, another interesting thing about these two images is that the moon really looks different during different phases. During a phase like this, like a first quarter phase of the moon, we see that because the sunlight is coming in from this direction, right? So the sunlight is coming in from this direction, and it's casting shadows that really allow us to clearly see the craters in dramatic relief, okay? Whereas when we look at a full moon, a phase of the moon being a full moon, the sunlight is coming straight in, right? So it's coming straight in from you towards the screen, and that makes a washed out image. We can't really see the shadows at all, so we don't see really any clear craters. But what it does is it really calls up the contrast between the less reflective Maria and the more reflective highlands. So it makes the contrast more obvious, but it really washes out the craters. So different phases of the moon, different things we can focus on, right? With a small telescope, a hobby telescope, or even a pair of binoculars. All right, you can see some of this with the naked eye, but not quite, right? You need some sort of magnification. Now back to the cratering, though. Okay, so the cratering on the moon has varied over time. How do we know that, right? Well, if we think about cratering, right, it hasn't been steady in time, but it's been fairly steady for the last 3.8 billion years. So we've kind of had a steady rate of cratering. So we'll say for the last 3.8 billion years, cratering, that's kind of the frequency of impacts, has been steady. Cratering, steady. Now, scientists have arrived at that number, and we're going to speak briefly about how they have, but what does that mean? Well, that means that there's a certain probability of having a very large impact, like this one that has survived in Arizona, in the deserts of Arizona, right? A big enough impact that it creates a large impact crater like this one, okay? So those happen with a certain probability every 50 million years or so. And so then, or we can look at smaller ones, right? So we have a probability of small impacts happening every 1 million years. We have the big impacts only happening every 50 million years, excuse me. And then the extra large impacts happening only every 200 million years, okay? Or some of them only once per billion years. So we see that trend throughout worlds in the solar system. So it allows us to really think about, okay, well, since we see this consistent trend between the different sizes of craters and how many there are, this can really allow us to date things. Because if a surface has a crater like this, then we know that this, for example, this region of Arizona has not been, say, covered up by lava or, pushed under another plate, to plate tectonics on Earth in at least as much time since a crater like this was likely to have formed, right? So it's a rough way to date things. Now we can confirm that dating with radiometric dating, like the rocks that we've brought back from the moon. We can actually study them, like this rock here, and radiometrically date it, and that can confirm, say, the age, in this case, of the Maria. And we date it back to about 3.5 billion years old. Okay, so we can definitely, have this confirmed method of using cratering to date things. But here's the interesting idea: is that idea of having about 3.5 or 3.8 billion years, so somewhere right around here, of pretty steady cratering. See, this is the rate of formation of impact craters. And see, from about this point, about 3.8 billion years ago, yes, it still was falling off a little bit, but then it's been very steady that whole time. Okay? So very steady amount of cratering. But why do we think it jumped up before that? Well, this is why. Because the Maria formed before. Okay, so the Maria formed about, I said it was 3.5, I misspoke. The Maria formed almost 4 billion years ago. And when we look at the Maria, we see that they have fewer craters, but about 10 times fewer craters than the highlands. Okay, so when we look at the highlands and we look at the Maria, we see that the number of craters, so we'll say number of craters in the highlands, equals about 10 times the number of craters in the Maria. But if we had a steady rate of cratering, that would mean that the highlands are 10 times older. Because if it's, that would work to date something that got cratered between 1 billion years ago and 2 billion years ago. Sure, absolutely. Just find out if there's twice as many craters, and it must be twice as old. But it doesn't appear to work, because clearly the highlands are not 10 times older than the Maria, because we've radiometrically dated the Maria at about 4 billion years old. That means the highlands would have to be 40 billion years old. It is impossible that the moon is 40 billion years old, because the Big Bang happened 15 billion years ago. That means that space itself didn't even exist 40 billion years ago. So we can absolutely confirm that the rate of cratering could not have always been constant. And then what's happened is astronomers have observed this inconsistent rate of cratering throughout the solar system. And it actually turns out that from about 4.2 to about 4.6 billion years ago, so for about 400 million years, 500 million years, there is this very special era of the solar system called heavy bombardment. Basically, it makes sense because this was the primordial solar system. This was before a lot of the like smaller asteroids had clumped together. There was a lot of leftover matter in the solar system. The gravitational pulls of big planets like Jupiter hadn't kind of cleaned up certain parts of the solar system. There was just a lot more leftovers, a lot more things to crash into the early worlds that had formed, the worlds like Earth and its moon and so on. Okay, so very, very fascinating idea that there had to have been a very different amount of cratering early in the solar system, and then for the dominant part of the solar system, the rest of the age of the solar system, it's been constant. Okay? All right. So now we're going to move on from the moon. Okay, well, we won't talk as much about Mercury, but now we're going to shift our focus to Mercury. Now, Mercury isn't as close to Earth, so we don't know as much about it as the moon. We've never set foot on Mercury, and it would be very hard to do so because of the incredibly high temperatures there, very, very hot and very cold. But Mercury does share some similarities to the moon. Okay, it orbits the sun. It's an actual planet, and it's a proper planet in terms of its orbit and its size. Unlike Pluto, which is a dwarf planet, Mercury is a real planet. But Mercury is a dead planet in that it has no active volcanism, it has no plate tectonics, and it just has a surface covered in craters. Okay, very much like the moon. All right. In fact, let's compare. Right, so here is the mass of Earth as 1. So we can see then that the moon is about 1% the mass of Earth, okay? And we can see that the Mercury is about 5% the mass of Earth, okay? We can look at the diameter of the moon. Now the diameter of Earth, so D for Earth, is about 12,000 kilometers. All right. We can see that the diameter of the moon is only 3,476, so less or about a fourth the diameter of Earth. And Mercury's a little bit bigger, but not much bigger, right? Mercury's a very small planet. It is the smallest planet, okay? We can see that the density of the moon is actually quite low at 3.3. The density of Earth, there's rho, the density symbol, is about 5.5, okay, grams per cubic centimeter. The density of the moon is significantly lower, okay? Mercury is almost as dense as the Earth, okay? The interesting thing about Mercury, when we look at Mercury here, all right, we see that Mercury has a very large core that is mostly metal. In fact, that's one of the famous things about Mercury is that it's a mostly metal planet. It's hypothesized that the reason that Mercury is mostly metal is because a large impact shaved off a lot of the material on the top, and that material achieved escape velocity and never got redeposited onto Mercury. And in fact, as far as that goes in terms of large impacts, I do want to briefly mention a bit about the history of the moon, the origin stories of the moon. Because if Mercury is mostly metal, has a mostly metal core, and has a very thin mantle, right? So very little rock on Mercury, because a large impact threw that rock off, that same story actually can explain how the moon formed. In this case, the impact occurred on Earth. Earth lost a lot of rock, a lot of mantle. That rock got thrown into space, a significant amount that could explain a mass that is, that is this large, all right? That's right here, yeah, this large. So models suggest that a large enough impact at about the limit of a biggest impact that Earth could have sustained in its early, almost molten phase, and this impact would have basically made Earth fully molten because so much energy, all the rock would be in a melting state, lava all the way through, top to bottom, right? Big molten ball of lava, which was the early Earth. Well, that an impact with a Mars-sized planet, maybe a rogue planet of some sort, early solar system, would have flung mass off, and then that mass became the moon. A moon with that amount of mass, and that confirms this density as well, because the density of the moon being so much lower suggests that it was formed from not the same concentration of heavier and lighter elements like the four terrestrial planets: Mercury, Venus, Earth, and Mars. And so there has to be some explanation about why the moon is so much less dense. And the fact that it formed from a large impact with Earth helps explain that. Okay? Now, the textbook also gets into why that impact theory for the origin story of the moon, the best hypothesis, is better than other hypotheses like us capturing the moon, because it's just, those ones just don't hold up. There's no scientific basis for any other explanation, all right? Any other hypothesis. So by the way, the surface gravity on the moon is about 1/6 that of Earth. The surface gravity on Mercury is just under 40% that of Earth. All right. We can see that the escape velocity for the moon is only 2.4 kilometers per second, so quite slow. And that's why it's feasible for China, for example, to land that probe on the moon and actually be able to launch it back off of the moon. The escape velocity for Mercury is twice as much due to that higher density and larger size. And then interestingly, the rotational period for the moon matches, about a month, right? That's how long its day is. That's how long it takes the moon to completely rotate around on its axis. And the fact that this is about a month is the reason that we say that the moon is tidally locked, and that one face is always visible to us, okay? And one face is always invisible to us. But look at the rotation period for Mercury. That's also a very strange rotation period. 58.6 Earth days. My goodness, right? Why does it take Mercury so long to spin around its own axis? Well, there's actually something really interesting going on with that Mercury rotation period, okay? And we'll come back to it in just a moment. Now, for a long time, astronomers thought that Mercury, with that very slow rotation period, was actually tidally locked to the sun, just like the way that our moon is tidally locked to Earth. In other words, the Mercury had one face that always faced the sun and one face that always faced away, which you imagine one side of Mercury to be incredibly hot because Mercury is so close to the sun, and the other side would be quite cool, all right? And that is the case. The difference between daytime temperatures and nighttime temperatures on Mercury are about 600 degrees Celsius. That's the difference. So there certainly are very huge temperature differences on Mercury, but there's not one side that's always hot and one side that's always cold. It turned out with modern technology, we were able to use Doppler radar to show that Mercury has a rotation period that is almost pretty much exactly 58.65 Earth days long. And we know we can very easily observe how long it takes Mercury to go all the way around in orbit. Okay, we don't need any fancy Doppler radar to do so. And we know that the orbital period is about 90 days. So 90 Earth days orbit. Okay, so clearly 90 does not equal 58.65. It turns out that Mercury is not tidally locked to the sun. Okay, and just a bit more about this Doppler technique. The idea is that radio waves are bounced off of a planet like Mercury or any object in space, and then the rotational period of that planet then can be recorded based on the spread of the signals, because there is a Doppler shift on the side that's rotating away from us, and that side that would be red shifted. All right, because the light there would be red shifted, and of course radio waves are a type of light. And then the side of the planet that's rotating towards us, that would be blue shifted. So that means whatever frequency signal of light, in this case radar, so it's like radio waves, so long wavelength light, but whatever frequency or wavelength was sent to the planet, what would be bounced back and then would be picked up by a receiver, well, then we'd find that there would be a spread of the original signal. And how spread out that original signal will tell us how quickly it's rotating. So slow rotation is less spread in this case, and then fast rotation is a larger amount of spread in the frequency or the wavelength. So that's the principle behind actually measuring very accurately the rotational period of a planet like Mercury. Okay, so modern science allowed us to find this number, 58.65. Okay, so here's the amazing thing though, is that we got the fact that the Mercury year is 90 Earth days. Okay, that's the time to go all the way around. Okay, so to go all the way around takes 90 Earth days. That's an orbital period. And again, that's really easy to observe, right? I mean, ancient astronomers knew the orbital period of Mercury. Okay, but now we know that the sidereal day is about 60 Earth days. We're going to round here, okay? Because I want to explain the amazing fact of this. So this means that there is a 2 to 3 resonance, okay? 2 to 3 resonance. And what I mean by that is that the sidereal day of Mercury is 2/3 the length of its year, okay? Now, this is the idea of, this is almost like tidal locking, because there's a perfect ratio here. Okay, and that's, again, it's pretty darn perfect, because if you look at the ratio of the moon between its orbital period and its rotation, it's a 1-to-1 resonance. Okay, but this one's a 2 to 3. First time we ever saw it in our solar system. Okay, so, and it's probably a resonance that exists in other solar systems. But what's so fascinating about it is what it really means for the day on Mercury. So let's zoom in and consider a day that starts right here at noon on this location on the surface of Mercury. Well, we know that the day is about 60 Earth days long, okay? Now, again, that's what I call the sidereal day. And if you forgot what the term sidereal means, a sidereal day is how long it takes a planet to rotate around and be facing the same way relative to a fixed background. In this case, the page, right? So the idea is that if we look at this red arrow, a sidereal day will be the time for that red arrow to go all the way back around and be facing the same way, which of course will take us to day 60. See? Because the red arrow has rotated around in quarter steps from day 1 to day 15 to day 30 to day 45 to day 60. That has completed one sidereal day, but not a solar day, because a solar day is the time for a planet to rotate all the way back around and be facing the same way relative to the sun. Now on Earth, there's not that much difference between our sidereal day and solar day. The difference, as you may remember, is 4 minutes, okay? But on Mercury, it's a very dramatic difference, and let's see why, okay? So let's start at day 1 at this location on Mercury, right at noon. The sun is directly overhead, as we can see right here, okay? Well, at day 15, all right, so, these are Earth days. So day 15 would be 1/4 of a sidereal day later. We see that the sun is kind of moving lower in the sky. All right. Day 30, we can see that the sun is kind of about to set, right? It's in the evening. And then at day 45, there's sunset, okay? And then by day 60, we're well into nighttime, all right? We've completed one sidereal day. But we definitely haven't completed the solar day because at this point we're well into nighttime. We're facing away from the sun at day 60. So we have to carry on to day 75 and then over to day 90, and we're at midnight, okay? So that means when we started at noon, which is, well, the beginning of our sidereal day, well, then when we came all the way around after 1.5 sidereal days, we're at midnight in terms of our solar day. Because if you think about it, these terms, noon and midnight, those are solar day terms. They're relative to the sun, not the sidereal day. Sidereal day is always already 1.5 times over, okay? But we've just got to midnight. Well, that's kind of interesting, isn't it? And again, all we're doing is just tracking the arrow. Notice I changed the color from red to green when we went from day 75 to day 90. That's because now we start our second Mercury year, okay? So all the red arrows are the first Mercury year, but now we're starting our second Mercury year, all right? And so we'll go ahead and go to day 105, all right, still in nighttime, day 120, still nighttime. Finally, at day 135, okay, we have sunrise in terms of the solar day. Then the sun continues to rise in the sky at day 150, getting higher in the sky at day 165, and finally at the day 1, which now we got all the way back around to day 180, we have actually finished our solar day because we've got back to pointing the way we were when we started, okay? So in other words, we're back at noon. So what we see that the third year begins on day 180, which means that a solar day is exactly 180 Earth days or 2 Mercury years. Isn't that a weird idea? To have a solar day that is twice as long as a year? Well, that's what happens when you have this type of resonance with this type of planet and a very slow rotation around its own axis. And it's real. It's amazing. Right? It's just so amazing these things exist in our solar system. And if that wasn't enough for Mercury, it also has a highly elliptical orbit, as we can see here. It has the only substantially elliptical orbit in the solar system. Almost all the other planets have very low eccentricity, but the eccentricity of the orbit of Mercury is about 0.2, which means it's fairly elliptical. It's not circular, not even close to a circle. And it actually looks about this dramatic. And that means that the sun is much larger in the sky when Mercury is closer. And that means that if you consider like another location on Mercury's surface, say this location, well, this location has noon over here. So that means that noon at that location on Mercury will always have a sun that is noticeably smaller, only about 2/3 the size in the sky. All right, so this elliptical orbit has a really big effects on different surfaces of the planet, having apparently a different size sun at different times of the day. Furthermore, because of conservation of energy, Mercury is moving much more quickly. So the velocity of Mercury is much greater when it's close to the sun and much slower when it's further away. All right, so these are velocity vectors in red. I'll fill them in like this. All right, so we'll call this velocity when it's closest and velocity when it's furthest. And because of that, because the velocity becomes so great when Mercury is closest to the sun, it actually starts orbiting faster than it's rotating, and the sun will drift backwards in the sky for about half an Earth day. So for about 12 hours of time, right around noon for this location on Mercury's surface, the sun actually drifts backwards in the sky because Mercury is moving faster in orbit than it's rotating. Okay? So Mercury is truly a remarkable planet. Here's a look at the surface of Mercury with some lower regions, all right, around its poles and highlands shown here. So there's basically low regions, some existence of lava flow, not quite Maria in the same sense, but there are low regions on Mercury and highlands. Some regions cratered more than others. And also at the poles, if we zoom in here, we can actually see there are craters that never receive sunlight and have liquid water, or not liquid, but they have frozen water. They have ice, water ice, okay, in the craters near the North Pole, because this is the North Pole right here. And that's because Mercury has almost no axial tilt. Unlike Earth with its 24.5 degrees of axial tilt, Mercury is basically straight up and down, and so its poles never receive direct sunlight. All right. Here's a large basin showing less cratering, or craters on top of craters. And this is the interesting thing. At some point following heavy bombardment, so after the first 500 million years of the solar system, Mercury, we think, cooled dramatically and actually shrunk and created these large scarps, which are huge chains of cliffs, as the whole planet shrunk and sort of crumpled up on its surface. And these large scarps will cut across craters because a lot of cratering occurred before the shrinking of Mercury. All right. Now, the last thing I'll say about Mercury is that Mercury isn't completely geologically dead. It still appears to, with its high metal content and higher density, have a small liquid core. The reason we think that Mercury has a small liquid core is due to, right, so small amount of liquid, due to the fact that it has a weak magnetic field, okay? So it actually has some magnetic field lines, and with those magnetic field lines, it has a tiny atmosphere. So like the moon that has no atmosphere to speak of, Mercury does have a tiny atmosphere. And that atmosphere is continually generated by the solar wind, which is a bunch of charged electrons that come in from the sun, the solar wind. And that solar wind comes in, hits the rocks on Mercury's surface, breaks free small chemicals, small molecules that then actually create a very thin atmosphere. And that atmosphere then is retained by the weak magnetic field of Mercury. So it's actually kind of interesting to think that Mercury does have a magnetic field and a small atmosphere, despite being so small. All right, well, that concludes the lecture. It's the last thing I wanted to say about Mercury. Thank you so much for watching. I hope this lecture has been interesting and informative.